Hello, ladies and gentlemen. In this video, we are going to try out some tricky integration problems that involve the derivatives of inverse trigonometric functions. Before we launch into some integration problems, we are going to take a quick look at the derivatives of the inverse trig functions, at least the inverses of the three major trig functions, sine, cosine, and tangent. Let's first take a look at a sine wave. Y equals sine x is in blue in this graph, and it does not have an inverse because it is not a one-to-one function. In order to define the inverse of sine such that it is a function, we need to restrict the domain of the sine wave. Let me explain a little further. If you have some function called f of x, then an inverse works like this. If f of a is equal to b, then if it has an inverse, the notation looks like this. It looks like exponent of -1, but that means inverse of f is equal to a. It is a function that does the opposite or undoes what an original function does. And here's the problem with a sine wave. If we say that f of x is equal to sine x, we're going to run into some problems. For instance, f of 0 is equal to 0, but f of pi is also equal to 0. If we try to evaluate f inverse of 0, we're going to have two possibilities. F inverse of 0 could be 0. F inverse of 0 could also be pi. This breaks the rules for functions. It breaks the vertical line test. It is not one-to-one. In order to make this work, we have to make sure that for every input of the sine function, there is only one output. The portion of the sine wave, the blue sine wave in the middle in red, is called cap sine of x. If instead we say that f of x is equal to cap sine of x, then we are allowed to say that there exists an inverse. The domain of cap sine of x is x, such that x is between pi over 2 and negative pi over 2. The range of cap sine x is f of x, such that it is between -1 and +1. Cap sine x then will have a domain of -1 to 1 and a range of negative pi over 2 to positive pi over 2. And it will look something like this. If g of x is the inverse of cap sine, then the domain of g of x is going to be x, such that x is between -1 and 1. And the range is going to be g of x, such that g of x is between negative pi over 2 and positive pi over 2. Furthermore, this function has a derivative, g prime of x, and it is equal to 1 over the square root of 1 minus x squared. Let's take a quick look at where this comes from. So we'll take a look at a geometric argument for the definition of that derivative. Let's start with a definition. G of x equals inverse sine of x and a right triangle to help visualize the idea. By definition, if g of x is equal to inverse sine of x, then x is equal to sine of g of x. Inputs become outputs, outputs become inputs. This is the nature of inverse functions. In this scenario, then, the angle, I can choose any of these other two angles, is called g of x. And the sine function determines a ratio, which we can call x over 1. X over 1 is sine of g of x. Sine represents opposite divided by hypotenuse. So x is my opposite, 1 is my hypotenuse. We can then use implicit differentiation. We take the entire equation, x equals sine of g of x, and differentiate it with respect to x. This is going to help us determine the derivative of the inverse of sine. The derivative of x with respect to x is just 1. And the derivative of sine of g of x requires the chain rule. We end up with cosine of g of x multiplied by the derivative of g of x with respect to x, which I'll just call g prime x. This is what we're looking for. If g is inverse sine of x, then g prime is what I want. G prime is equal to 1 over cosine of g of x. Cosine is adjacent over hypotenuse. So we need to define the adjacent side of this triangle. What is this side right here? We can use the Pythagorean theorem to define this as 1 minus x squared. Cosine of g of x then is adjacent over hypotenuse, which is the square root of 1 minus x squared over 1. And my definition is set. This is the derivative of the inverse of sine. A very similar process can be used to figure out the derivative of an inverse cosine function. We won't go through all the steps again, but let's just take a quick look at a cosine wave and a cosine wave with a restricted domain. Once again, a cosine wave will only have an inverse if we restrict the domain. If f of x is equal to cap cosine x, we can limit the domain from 0 to pi to ensure that this function has an inverse, which will look something like this. The inputs become outputs, and the domains become the range. G of x is the inverse of f of x. Then its domain stretches from -1 to 1. And this also has a derivative. It's very similar to the derivative of arcsin. -1 over the square root of 1 minus x squared. Last but certainly not least is cap tan x. We won't go through the steps of showing the tangent graph or cap tan x. For the sake of just getting to some integration problems, I will list the derivatives here. Here are the 3 derivatives of the major inverse trig functions. Arc cotangent, arc secant, and arc cosecant also have their own derivatives defined, but for now we are just going to stick to these 3. The first problem we'll take a look at is example 5 from section 7.5 in the textbook, which asks us to evaluate the following integral. 2x over the square root of 1 minus x to the 4th. Part of what makes these problems so tricky is recognizing when there are inverse trig derivatives involved. We may try to attack this by using the substitution method or something like that. If we do this, we're just going to run into a dead end. We ended up with -4x to the 3rd. which actually doesn't do us any good. We have a 2x up top in the numerator. It would just be a dead end. Instead, we take advantage of the fact that this looks a little bit like the derivative of arcsin. If we split this fraction up into pieces, it looks a little bit more like the derivative of arcsin. Now it might be useful to think about this in terms of substitution. If we allow u to be x squared, then a little bit of magic is going to occur. In the denominator, we will have 1 minus u squared instead. If u is x squared, then du is 2x dx, which, sure enough, shows up in our integral, and we can continue to rewrite. Now that we have everything in terms of u, we can take another look at this. Now it's exactly like the derivative of arcsin. Arcsin specifically of u. Replace u, and we have our final answer. This problem was an indefinite integral. Let's take a look at a similar problem that is instead a definite integral. This will be example 6 from section 7.5. We are asked to evaluate the definite integral of -1 over the square root of 1 minus x squared from 0 to 1/2. This problem requires very little work up front. -1 over the square root of 1 minus x squared is the derivative of arccosine. So already we know we are going to be evaluating arccosine x using the fundamental theorem of calculus. We need to evaluate arccosine of 1/2 and arccosine of 0. Basically what we need to know is cosine of what number is equal to 1/2 and cosine of what angle is equal to 0. Arccosine of 1/2 is pi over 3. Arccosine of 0 is 1. And this gives us our final answer. Although our final answer is incorrect. Arccosine of 0 is not 1. That's crazy. Arccosine of 0 is, in fact, pi over 2. My mistake. This will give us an answer of -pi over 6. Example 7 from the book is going to be a problem that deals with arctan and the derivative of arctan. We are asked to find the derivative of y with respect to x when y equals arctan of x squared minus 2. This is actually not an integration problem. This is a straightforward derivative problem. They also include a point for us. At the point, 1 pi over 4. If we think about this in terms of the chain rule, we can say that the outside function is arctan x. The inside function is x squared minus 2. The derivative of the outside function is 1 over 1 plus x squared, and the derivative of the inside function is 2x. The chain rule follows f prime of g of x multiplied by g prime of x will give us this result. 1 over 1 plus, and we are going to square x squared minus 2 multiplied by the derivative of g of x. At x equals 1, we just end up with 2 over 2. Final answer, 1. Now that we've taken a look at a derivative problem that uses arctan and the derivative of arctan, let's do the opposite process. Let's integrate with arctan. We are asked to evaluate the definite integral x over 1 plus x to the 4th from 0 to 1. Again, your first instinct might be to use the chain substitution. You might try to say that u is equal to 1 plus x to the 4th, but this will lead to a dead end. 4x to the 3rd doesn't really help us out. We need to recognize when a problem involves the derivative of one of these inverse trig functions. So let's get rid of this, and let's try something else. This looks more like the derivative of arctan than it does the others. We can make it look more like the derivative of arctan by separating the fraction. Now we can think about this in terms of substitution. Let's let u equal x squared. Now we're integrating from 0 to 1, 1 over 1 plus u squared times x dx, and we're hoping that when we take the derivative of u, we end up with what we want. And we end up with something very close to what we want. We have 2x dx. The problem includes just x dx. So I'm going to stick a 2 in there, stick a 1/2 on the outside, and now we are ready to roll. This is now 1/2 of the integral. 1 over 1 plus u squared du. All in terms of u now. This antiderivative is arctan. So we are going to do arctan of u. U is defined as x squared. We're going to do 1/2. We're going to evaluate this from 0 to 1. And when we're all done, we're going to multiply it by the constant 1/2. Tan of some number is equal to 1, and tan of some number is equal to 0. This is a way of thinking about evaluating arctan expressions. Tan of x is equal to 1 when sine of x equals cosine of x. And that happens at 45 degrees or pi over 4. Tan of x is equal to 0 when sine of x is equal to 0. And that occurs at 0 degrees or 0 radians. Final answer then is 1/2 times pi over 4. The last example is quite tricky, so let's dive right in. We are asked to evaluate the indefinite integral 1 over x squared plus 6x plus 13. without a little initial push in the right direction, you might once again consider trying to integrate this expression using a substitution of u equals x squared plus 6x plus 13. But once again, it will lead to a dead end. You're not going to have anything to do with this 2x plus 6 dx. There's going to be no good way to rewrite this expression only in terms of u. It's going to be very difficult, if not impossible, to eliminate the x's. So you need another strategy. It's going to involve the derivative of arctan. In the derivative of arctan, we have 1 divided by a number plus something squared. The number happens to be 1, but that's what we're looking for. A number plus something squared. We don't quite have that. We have a number, we have something squared, but we also have this thing in the middle that makes us sad. So if we could somehow rewrite this with no 6x, then that will make us happy. So we're going to accomplish this using a trick from algebra called completing the square. We're going to take this numerator, which is a second degree polynomial, it's a quadratic, written in standard form, and we are going to rewrite it in what's sometimes called vertex form. The process of completing the square is pretty straightforward. We want to take this middle coefficient, split it in half, and square it. That gives us the number we require to complete the square. The 13 is still there. In order to add 9, we need to subtract 9. Now we can rewrite this as something squared plus some number. It might be better to switch directions. Some number plus something squared. Now, our indefinite integral looks a little bit more like the derivative of arctan. Not quite there yet, but we're closer than we were. The derivative of arctan calls for 1 plus something squared. We have 4 plus something squared. So we have to get rid of that 4 somehow. We're going to do this by multiplying each term in this quotient by 1/4. So we're going to take the 1 on top, and we're going to multiply that by 1/4. We're going to take each term in the bottom and multiply it by 1/4 as well. We're going to take the 4 and multiply it by 1/4. And we're going to take the x plus 3 squared and multiply it by 1/4. This cleans up a little bit. The 1/4 on top can come out. We're still left with just 1 up top. This becomes 1, just like we wanted it. And then we have x plus 3 squared over 4. We've got our 1 here, which makes us happy. The derivative of arctan includes 1 plus something squared. So we have our 1, and that's good. And then it calls for something squared. Well, we almost have that. We had it before, but this multiplication by 1/4 actually set us back a half a step. We have something squared over 4. Something squared over 4. So in order to fix this, we have to get the 4 involved with the square. We can do this by rewriting 4 as 2 squared. We rewrite again. 1/4 of 1 over 1 plus something squared. The something is x plus 3 over 2. Now we're in business. It took a while, but we made it. If we allow u to be x plus 3 over 2, then du is 1/2. We need 1/2 dx inside our integral. We only have dx, so let's put a 1/2 dx in there. And in order to counterbalance that, we'll multiply the outside of this integral by the constant 2, or 2/1. We rewrite, perhaps one last time. 2 times 1/4 is 1/2. Now we can define this integral in terms of just u alone. 1/1 plus u squared du. This was the goal all along. This is the derivative of arctan. 1/2 of arctan of u, where u was x plus 3/2. Indefinite integral plus c. There you have it. That one was very tricky. I hope you were able to follow along, and I wish you the best of luck as you attempt some problems on your own. Goodbye.